I'm going by my phone. I think my phone has the more accurate time. Okay, I think it's officially 2 o'clock. Again, I'll look into what's wrong with the internet time on this machine later on. But welcome back, everyone. We're at a pretty exciting point in this course. We did a lot of hard work in Chapter 2, developing the theory of limits. And now in Chapter 3, Section 3.3 is the big section which bridges the gap between defining the derivative as a limit and then finally showing what the actual differentiation formulas look like so we can start streamlining our work and calculate derivatives in an efficient way. For example, the punchline to section 3.3, which we'll look into again, is we have a function that's of this form. This is a degree 3 polynomial. Then finding the derivative is a matter of messing around with the exponents. The derivative of this function f first takes the power 3 by the red dot, multiplies that 3 there to give us a coefficient of 9. The new power is 1 less when we differentiate. Then when we repeat on this term, power 2 comes down, multiplies the negative 12. So we get negative 24, and the new power is 1 less. So that's really x power 1, which just simplifies to x. And the final thing that we discovered or discussed was if that's a constant, its derivative should be 0, which it turns out to be is true. And so we get just that as our total derivative. This is in stark contrast to the way we do derivatives on our quiz 3. Well, any questions, folks, about our announcement so far? Okay, and I did notice there was some confusion about quiz 3. So just mentioning a little bit more about that. Quiz 3 was officially assigned at the end of this week, September 16th through the 22nd, but I didn't feel like we got far enough in section 3.1 to really justify that quiz. So I pushed it back to be officially assigned on this week. I moved the due date here to October 2nd, which is the right due date. But then the thing I messed up, I finally put a correction on it, was I didn't put the right due date on this document. It still had the old due date saying, I believe it was September 25th. So this has just got updated. And if you turned your quiz in early just to try to get in before the due date and you'd like to revise it, I will accept corrections on that if you decide that you need to rewrite that. But that's the official due date. And sorry again for the confusion. I finally got the PDF actually updated. So our quiz 3 is just that one there using the definition of the derivative. Then we're going to play around using differentiation formulas in section 3.3, and that's what our quiz 4 is likely to be about. Well, that's my full set of announcements, folks. Aside from if we look a little bit further in the schedule, next week is midterms week, but again, there's no special assignment or a special exam. Our second exam is going to be right in October 14th. So that means just this weekend, right around this date, the 3rd and the 4th, I'm going to start putting in information about exam 2, the coverage, review materials, and those kinds of things. So this is where we're at. That's where we're going down below in the schedule. Any questions whatsoever, folks, before we get started? Okay, well, let's jump right in. We left an application problem before we went on the weekend. So this is our place to start. Kind of a rough problem for our very first problem of the day. But you know what? This is a good one because at least it's justifying why we're taking all the time to develop theory of limits and then defining a derivative. This is one of the really good applications that we're going to be looking into more and more in chapter 4. And so this is where us getting a kind of an early start on how this all works. A problem like this, just as you see it, is a common question on exam 2 and potentially the final exam as well. So here's how this problem goes. They tell us biologists have proposed a cubic polynomial to model the length L of an Alaskan rockfish. So if you need to get kind of some context going on that, you can always take something like this, right click on it, go search Alaskan rockfish, and it takes a moment, but eventually you get some good pictures Oh, that looks like it's delicious. So this is what we're getting into. We're modeling the length of these things, if those are indeed Alaskan rockfish on the right. So the length of the rockfish at age A is given by this length function here. It's cubic because of the degree 3 on A there, and, well, 4 terms altogether. L is measured in inches, A is measured in years. We want to calculate that derivative, dLdA, evaluate at A is 12. Then this is, to me, the major thrust of this problem. It's more about giving an interpretation to what we just calculated after we find the derivative. So that's the big takeaway right there. Any questions, folks, about the model before we start working with it? Okay, and like I mentioned, this is kind of a tough problem to run into right after a weekend. So let's maybe do a warm-up just to start us out. So here's our warm-up. Let's say here, let f of x be equal to a cubic polynomial like this one, but just a little bit more easily managed. So we don't have a nasty one for our first day, or first problem of the day. Let's say this just goes x cubed minus 2 x power 2 plus 13x minus 11. So there's our degree 3 cubic polynomial. If we're calculating dLdA, but we use Newton's prime notation, instead of writing that portion, we write f prime of x. But however we say it, whether we're using Newton's prime or Leibniz notation down there, we're just indicating the derivative. Well, here we get to use the power rule. Anyone have the first term after you differentiate x cubed? We would absolutely get an x squared. Good call. The first thing that happens is the 3 would come down as a coefficient. And then as Dana and Doug said, the new power is just x squared. So the power 3 just comes out in front like this as a coefficient, and then that's our result. So that's pretty much the name of the game. We're just going term by term. Let me highlight the next one we're on, and differentiating in that way. So green is indicating the term we're about to differentiate. Below in blue is the differentiation result. How about another set of volunteers for this one? Anyone see what that would turn into as a derivative?
Minus 4x.
Good call, Alejandra. Absolutely. So the coefficient of 2 right here multiplies that negative 2, so that's where we're getting that negative 4. New power of x is x power 1, and there's nothing wrong with writing x to the power of 1, but I like how you just said x. It's good to just put it in its simplified form right off the bat. So one last term to go. Any last volunteers from the class on doing that term there? What would we get after differentiating the degree 1 term, 13x? Good call, Eli. This one turns into just 13. And honestly, I think this one is hard to visualize. So let's maybe put down something up here to kind of justify it. But you're absolutely right. It is 13. There's 2 ways to think about it. First thing you might think of is that's a linear function. You can plot it in the plane, and its slope would be, in fact, 13. So that would be its result. But if you're thinking in terms of the differentiation formulas, here's the way to justify it. If y is equal to 13x, we're using the power rule just like we did on the first 2 terms, but notice that there's no power actually exhibited on that x. So to really crank it out with the power rule, you might want to actually put a 1 there. Then next, y prime would say the coefficient of 1 comes down, multiplies at 13. So here's 13 times 1. The new power of x is always 1 less. So we come up here, subtract 1, and now it's to power 0. But then here's all the simplifications. This is 13 times 1 for just 13. x to the power of 0 is 1, so that's just 13 times 1 again. And so that means either way we visualize it, the derivative of that one is just 13. So plus 13 on that one. We're working through our differentiation rules so far. We've used the power rule, the difference rule, the constant multiple rule, the sum rule, another constant multiple rule, and here we're differentiating a constant. Any volunteers for that last part there? This one would turn into a 0. Good call, Alejandra. The reason this one is 0 is if that's a constant, it will always have derivative 0. Visualizing that one again, it would look like this. Y is the function that is negative 11. If we were to plot this on an xy plane, we would go down, this is going to be hard to see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I never seem to draw those long enough. But then the graph would just be this, a horizontal line at height y equals negative 11. The slope on this thing, anywhere you go, is always a slope 0 because it's a horizontal line. That tangent line is now horizontal. So now this part as a constant goes minus 0 or plus 0, same quantity. I think that one deserves highlighting since we usually went right down that constant there, minus 0, coming from the negative 11. But it's good to do occasionally just to remind ourselves that going from here to here is the derivative of a constant. And so it equals 0. So that's our warm-up for the day. Any questions at all, folks, on working through this problem here? Okay, thanks for the participations on going through each one of these terms right here and finding out what the derivative will be. Part of our goal in chapter 3 is really just to focus on this and practice this more and more. Limits still come back here and there in chapter 5, notably, when we turn to integration. But for the moment, we want to get really fluent with these kinds of rules we saw in this example, because these are going to be lots of common problems in section 3.3, 3.4, and so on. Well, let's turn next to our application here after that warm-up. Again, they're saying that the length of the fish is going to be modeled by this polynomial. It's just the same as the function up here, but think of a as your x when you visualize this problem. Let's put that down as a note. A is the independent variable. Which is like x. So when we go to differentiate this, every time you see a cubed, a squared, think x cubed, x squared, and so on, and you're on the right track. Coefficients are a little bit nasty, but we have a calculator that's available to us, so we'll make good use of this quick calculator here. Let me just put it in a good spot. There we go. So step 1 in this process, we have to calculate that derivative down here, dl dA. We could have called it L prime, and that'd be just fine. But in an applied setting, there's really good reasons for Leibniz notation, and we'll mention this after we calculate it. So dl dA, that's the derivative of the function length with respect to the age of the fish, A. But the way this is calculated is we take this 3 right here and multiply it against 0.0155. So I'll write it out first, then we'll throw it in the calculator. So on the notes, we'll have a paper trail of how it all actually came together. So 0.0155 gets multiplied by the old exponent, 3, coming from there where the red dot is. New exponent is power 2. Then rinse and repeat, much like we did on the example above. We take the old coefficient, negative 0.372, multiply it by the old exponent, which was 2, by that red dot. Then the new power of A is power 1. So I'll just leave that with a blank position here to indicate power 1. Lastly, when we differentiate this one, we're essentially just doing what we did over here with the 13x's circled in purple. The derivative of 13x just became 13. And likewise, the derivative of 0.395a just turns into 0.395. So plus or 3.95, sorry, I'm saying my decimals wrong, 3.95. So the pattern you can think about on this is, let me just reset this highlighting. If your variable has power 1, like the 13x there, you just take the coefficient upon differentiating. Likewise down here, a is like our x in this problem. Honestly, that's what makes these kind of confusing, new variables out of nowhere. But the power is 1 on a, and so all we do is take the coefficient when we go to the derivative. Finally, 1.21 is constant, so when we differentiate that part, it goes to 0. I'll plug down here plus 0 just to emphasize what happened with that last term. Well, there's a derivative. We still need to simplify it down. But any questions or comments, folks, on producing it? Okay, I have to say, I think these problems are always really tricky. And part of the reason is kind of a symptom of how we study these problems up here. We focus on x as a variable so often that when we go down to an applied setting, you almost always indicate the variables in ways that reminds us of the problem. A is the age of the fish, L is the length of the fish, for example. And so it always gets a little bit hairy during dealing with those kinds of problems when we're seeing these ones so often. So if this ever feels a little bit weird, start with a warm-up problem first, and oftentimes it can really clear up what the misconception might have been in differentiating the applied problem. But let's go and actually crank these out in the calculator. I have a coefficient 0.0155 times 3. So 0.0155 will replace with 0.0456. A to the power 3. And I should be able to do that one, but it's Monday, so let's make sure we get the coefficients exactly. 0.372. Instead of doing it in our head, I'll just do it that way, 0.744. That's going to be a minus 0.744.
Sorry, for that first value, wouldn't it still be a to the second power?
Oh,
Right.
yeah, where did I get that 3? Thanks for spotting that, Kaylee.
Okay.
So that right there, from here to here, I should have copied power 2. Well, other questions so far? Okay, so majorly, pretty much all I did so far in this step was made that correction there. Again, thank you for spotting that, Kaylee, as well as just calculating 0.0155 times 3. I typed that incorrectly, so that's where the 0.0456 came from. And then the 3.372 times 2 just turned into the 0.744 in that way. Well, we've got our function down. Thanks again for spotting those weird corrections. Usually my mistakes I make is a copy error. So 2 to 2 was that mistake on that one. Next thing we need to do is calculate this portion. Yes, absolutely. Thanks for mentioning that, Elif. So even if the powers here were negative, even if there was a square root of 2 instead of 2, same pattern is going to apply for each one of these problems. And that's going to be part of what we're doing down below in the notes. I have some odd looking exponents when we take a look at stuff like these, for example, or these. That kind of stuff is coming up with the further practice. Other questions so far? Okay, so when we did this part of the problem, all we were calculating is the derivative. Think L prime or dLdA in Leibniz notation. When we expand to this portion, all we're now essentially doing is taking that derivative dLdA. Up here it says plug in 12 for the age. You know, it might be a good idea to start color coding this up. Let's think of blue for the length of the fish and green for the age of the fish. So we're plugging in 12 there, and we can now say the rate of change of the length with respect to the age of the fish, now evaluated when the age is 12 years, equals all of this. 0.0456 multiplied by something to the power 2. That something is going to be the 12. It's just plugging in everywhere you see the a variable occur. So it's going to go into this location for 12 squared minus 0.744 times a power 1. So we'll throw a 12 right to that location. Then plus 3.95. So we want to calculate this thing, include units. First of all, let's just find out what all this is in the calculator. So typing that in carefully, we have 0.0456, 12 squared, minus 0.744 times 12, plus 3.95. Let me expand that just so I can make sure it's all in there correctly. Always good to double check here. 0.0456, 12 squared. Okay, provided we got all in correctly, we get a 1.5884. So that's our second step here. First, we differentiated using the power rule and the sum and difference rule. On this new step, we expanded to evaluating our derivative when a is 12, and we get that to come out. So finally, as far as the units go, when we go to state units, so let me get my tools here in the right spot. There we go. When we go to state units, that's part of what's brilliant about this Leibniz notation. It's clunky, it's hard to look at, but the more and more you work with it, the more it starts to make a little more sense, even than the prime notation, where we write f prime of x. So the units for this number, 1.5884, first inherits the unit from the numerator. When it said dl, we're referring to the length, and the length is measured in inches. So we'll come over here and say 1.5884 inches per, we come down below here, a is the age in years, so we will say inches per year. The per I just wrote as a fraction bar in this way. So it's a rate. A rate always has two units, a unit in the numerator, a unit in the denominator. And this one is how fast this is growing in inches per year so far. So we did this part of the problem. We calculated the derivative. We included the units. Next thing is to give a practical interpretation using the context. But any questions at all, folks, getting to that big step there? Okay, I'd say that's a pretty big step to get to that part of this problem. Again, it's a kind of a tricky problem for right after a long weekend. But once we're here, even though that was the big step, I would consider this part, let's leave this highlighted in gray, to be the most important part of the entire problem. Because that number, 1.5884, it's completely useless to us unless we know really exactly what it represents. That's always the hard thing in a math class like this one. Awesome, I'm really glad to hear that, Doug. I think an applied problem like this sometimes does bring things back together a little bit better than just doing derivatives like these that have essentially no soul as far as the context is implied. So this is, again, the major step for us. We're going to say what that number really represents. And first, let me say what the incorrect answer is. It's really tempting when you see all this to say the length of the rockfish when it's age 12 is 1.5884 inches. Well, that's not quite right because the thing on the left is giving us a derivative. So for an interpretation like this one, I would probably write out something about like this. Let's start with the age. When the fish is, let's mention the time, 12 years old, we get this number, Now, because that number is positive, we will say the fish is growing. If it was a negative number, we'd say the fish is shrinking. That may not make any sense in this kind of context, so it's good to have a sanity check there. I think that's tricky enough to deserve some highlighting. Let's mention here, we said growing because that number is positive. Okay, so putting this all together, we have Alaskan rockfishes we're interested in. This describes the length of the fish at any age, but that's derivative right down here by the red dot. Oh, excuse me, this one right by the red dot describes how fast it's growing at any age. So when we go to interpret this derivative, when we plug in 12, we'll say it's growing at a rate of 1.5884 inches per year. Once we go to 13 years, probably that number is even a little bit smaller. As things get older and older, the growth rate of the organism we usually expect to start to fall off as it reaches its age at maturity. So this is kind of like, again, the analogy of driving a car. You could say 12 minutes into your commute, this might be your rate of speed in miles per hour. It's not going very fast. Maybe you were braking at that time. And so this is always the rate of change at a certain time. Well, any questions at all, folks, with getting to that interpretation?
I have a question.
Yeah.
So if we weren't given 12 years, like if it was just at any age, how would we word the practical interpretation?
Oh, that is a really good question. I think that's extremely tricky. So let me take this down here. Let's make that like a part B to this question. So if we're just looking at this right here, we could think of this as at the age A. It's a little bit awkward because we can't specify the actual age like you're mentioning. So at the age A years, the rockfish is growing at a rate of 0.0456 a squared minus 0.744a plus 3.95 inches per year. So the resolution to that question is essentially we say the same thing, except here we got to put in an actual number, but down here we have to put in the function that depends on the number, whatever a could have been. Does that make sense with that question there? Awesome. Thanks for asking about that. Other questions with the either interpretation? Okay, and just to clarify the notes, let's put here in brackets that this is the interpretation when A is not specified. I would say that this is a good question too as well, and for the purposes of exams, if I was going to ask like we said here, this one's a common question for exam 2 or the final exam, I'd usually do it in this way, where you're plugging in a value and giving an interpretation relative to the age of the fish or the age of the tree or whatever the unit might have been for the applied setting. Well, other questions or comments at all? Okay, this is a tough problem, I have to say, but it's a good attack these kinds of problems early before we get into chapter 4, where these become more and more common. So also the bigger takeaway with example 3 is think of this as our first problem where we're really looking at it from an application, an honest, decent model. and just interpreting what the derivative will look like. So we'll look into those more and more often. They're challenging, so this is us just getting a head start on it. The major things you're going to be doing in the homework are really going to look a little bit more like this. You're just going to be given different functions, and you'll be told to differentiate them. So I put down some hints on these. Look before you leap, because some of these functions you can't actually differentiate right at the start. For example, this one is just fine. It's in an expanded form, so you can use the sum rule, the difference rule to break apart the additions and subtractions. But this one has a problem. If you look at the notes carefully, we don't yet have a formula for when things are being multiplied as functions. Sure, this -6 is multiplying x power 4, but for that, we have a constant multiple rule. It's this one up here. If you take a constant times a function, then your result is just take the constant times the derivative of that function. And we've been applying that to all the time so far. For example, if you have 7x cubed, the derivative is 7's unaffected, gets multiplied by the 3, and you get 21x squared. But there is no version of this rule so far in the notes that handles that kind of function, where a function of x is multiplying another function of x and another function of x. There are formulas that are going to help us out in section 3.4, but even when the formula would work for this, we still wouldn't use it on that function because expanding out the function, simplifying in that way, still makes better sense. So the punchline to these problems are, in section 3.3, we don't have a lot of formulas, but in 3.4, we have something called a product rule, here it is, and a quotient rule down the line. But this is an example where we should never, ever use the product rule. It's honestly just a waste of time. It's simpler to work with the function algebraically and differentiate. And we'll come back to this one. That's a case where you really do need a product rule. There's no way to FOIL that out and expand putting a plus or minus between the two functions x cubed and e to the x. So we'll come back to that one there. And that's the purpose of the thing highlighted in yellow. Sometimes calculus gets really challenging because these problems here were never intended to have a powerful differentiation formula attached to it. It was more just do a bit of algebra first. But let's give this a try here. Let me zoom in just a bit. Part A starts off as an ordinary nice function, y equals, so you could call this a y prime. Or you might say instead of y prime, dy dx if you're using Leibniz notation. These are always completely synonymous. They always indicate the derivative. And I'll be mixing them up in the notes just so that our eyes are trained to see one or the other. So over here for y prime, this is pretty much exactly what we were doing on the first problem of the day. We take the power 4, multiply -6 to get -24. Power in x is now just power 3, so one less. Rinse and repeat. The 3 there as a coefficient gets multiplied by 2, so now it's +6. No power of x is 1, so we'll just leave it like that. But we have to be really careful with -e power 4. This is essentially a trick question with that thing. Anyone see what that would go to as a derivative? I would say that that circled thing in orange is pretty challenging actually to differentiate. The thing that can happen on an exam, which is pretty common, is people might write 4 times e power 3, but turns out that's not the right derivative for that one. This one is one of those weird things where it becomes a constant rule. So we're back up to this formula up here. Sorry, my load starts to lag a little bit at the start. What this first formula says, the derivative of a constant is 0. And here's where it gets challenging. There's a lot of weird constants you can put in. For example, natural log 2 is also a constant. We can plot that thing to visualize it a little bit better. So let's do it right here. If we say y equals natural log 2, then that's our function. Anywhere you go on here, we have a horizontal tangent line, so the derivative is 0, and that's why we get a 0 derivative on that one. Well, that one's not so hard to spot as a constant because there's no x anywhere inside there. But this one, down below in the notes, again, is extra tricky. It's basically a trick question to watch out for. It's the power 4 on it that makes it look like we might be using a power rule. But that one's no different. If you say y equals e to the power 4, we get a value of 54.59. So my scale is not quite right to show that, but here it is once we zoom out enough. Just the same as natural log 2. Anywhere you go on this graph, the tangent line is horizontal, which would mean the slope of that tangent line is 0, but that then means the derivative of that thing is 0. So at the end of the day, the best way to spot a constant is x was just missing from that entire term. So let's say that here in the notes. X is missing. So this is a constant. Deserves an exclamation mark because, again, that one is really hard to spot, in my opinion. Because it's a constant, it goes to 0 in the derivative. Let's write it down here just to really emphasize that. And so our derivative is equal to y prime negative 24x cubed plus 6x. So that's our derivative there. Any questions at all, folks, on running through that one? Okay, well, let's give this one down here a try. Part B is a little bit challenging because everything is being multiplied. And let's put down a really fast warning on this one. Or maybe a caution. I'm not sure what the best way to say this is. Let's say caution. The derivative of f times g is not f prime times g prime. So that's what's going on here. Think of this as a function f. The next one is a function g, and x minus 3, a third function h. Well, the derivative of this is not the derivative of f times the derivative of g times the derivative of h. That's really kind of unfortunate. So instead, our strategy on this one is we must expand this expression. In these notes, section 3.3, it's pretty clear that that's what we've got to do. It's the only way to get the correct answer. But that problem becomes even trickier in section 3.4 because 3.4 does give you the right product rules, what we'll call it, to differentiate. So again, the takeaway on this is it's also important to analyze and decide what problems do we even want to use the product rule on. And it's not stuff like this because we can expand this one out. So let's get to the algebraic work of actually expanding it out. So far, I'm just writing f of x because we're not actually differentiating it. It's just ordinary algebra. We're going to have to expand root x, so we will write that one as an exponent. It's to the power 1/2. Next, we'll start foiling. 4x by x for 4x squared. 4x by negative 3 to get negative 12x. Next, we're expanding going this way. So there's minus 3x. Here to here is plus 9. And all I've done so far is FOIL that out. So let's combine our like terms in the middle. We have x to the power of 1/2. And although this is just fine as it is, 4x squared, let's change the exponent on that. This is 4x to the power of 4/2. Reason we're doing that is we're eventually going to multiply x to the power 1/2 inside the group, and the exponents add up. So we may as well get the least common denominator going. 4/2 reduces back to power 2. Then over here, we have negative 15x's. The power on that x is a 1, which we can write as 2/2. Again, just anticipating x power 1/2 distributing through. Finally, it's plus 9. And on our next step, we're going to distribute that x power 1/2. When it multiplies here to here, we get 4 x to the power of 5/2. Let me just fix my equality sign. There we go. So all that happens when we multiply x times an x is, think of the simple example. If it was x squared times x cubed, we would have gotten x power 7. But when we take x power 1/2 times x power 4/2, we're doing essentially the same kind of thing. Yeah, I get you, Douglas. This one is a weird one because the exponents are just kind of out of control. So the way to think about this is, if we're multiplying here to here, x squared times x cubed, then, oh, I made a mistake there. I had to add up my exponents. I'm not too sure what happened there either. That would have been power 5. So the exponents just add up in this kind of configuration. But now when we're multiplying x power 1/2 times x power 4/2, we take the exponents, 1/2 and 4/2, and just add them together. That's how we're getting the 5/2 right there. But those exponents are pretty wild. Just to help visualize this a little bit better, let me write out my next step in this way. Multiplying here to here, going in stages, would give us 4 x power 1/2 times x power 4/2. Finally, here to here is negative 15. X power 1/2 times x power 2/2. And then the last multiplication here to here is going to be plus 9. X to the power of 1/2. Any questions, folks, to this stage? Getting down to the expanded form? Okay, then the next rule I'm going to use for exponents, let's just state that rule in the margin, is x to the power of m times x to the power of n is x to the power of m plus n. That's the exponent rule that they typically state, but what they don't always say or emphasize is that m and n can be any real number whatsoever. It could be integers. That's the ones we're used to, like x squared times x cubed. But they can also be fractions. They could be irrational, all sorts of things. Cameron asks, how did you get x 1/2 without applying it to the rest of the function before foiling? Oh, thanks for asking about that, Cameron. That's another weird exponent law that goes like this. Let me indicate that one on the margin as well. So the one that's circled by the red dot with the purple pen on there goes like this. If you have a root x, then there's a different way to indicate that. If you really want to, you could call it square root x this way by saying the index is definitely 2. It's almost always implied if you leave it blank like this. And this one turns into x power 1/2. Then the general rule goes like this. If you have maybe, say, the nth root of x. So if n is a 3 here, the index, we're talking about the cube root. If it's a 5, we're talking about the 5th root. But this is just in radical notation with a little root sign there. If we want an actual exponent, we would write it this way. X to the power of 1 over n. So this root is special, but it's indicating index of 2. So that one turns into x power 1/2. However, in general, the nth root of x comes out that way. For a really quick example, if we had 5th root of x, that's just saying x to the power of 1/5. So that's what happened to that thing. We took the root x, but wrote it that way, just anticipating we have to expand everything through. So x power 1/2 had to eventually multiply through. But if we had, say, square root x right here times x to the power of 4/2 or x squared, those don't combine in a natural way. So that's why we changed it to x power 1/2 there. Dana asks, how did we get x 4/2 and x 2/2? Oh, that's a good question as well. Thanks for asking that, Dana. Let me reset the focus here. So we know what happened to this one. We have to make it become x power 1/2. Then we expanded all this and got those results. And then these two in the middle became the negative 15. But the larger question is, what happened to power 2? What happened to power 1? Why is it 4 halves and 2 halves? Well, the thought on that one was the moment we got to x power 1 half there, we have to make that 2 become 4 halves. So we just change our exponents around in that kind of way. Likewise, this was really exponent of a 1, an exponent of 1, but 1 can be written as 2 over 2. And that's how we got the 4 halves and 2 halves. That's pretty much what's going on. Good call, Doug. We needed everything to be over 2 because over here, when x power 1 half multiplies through, we have to add up those exponents. And so we were just arranging for the exponents to be added up in a really quick way. Everything had to have denominator 2. Does that make sense with that question about what happened to those exponents here highlighted, Dana? Awesome, glad to hear that. So to recap on this problem, it's really irritating, to be honest. If they had just normal powers, say this was x power 2, right where the root x is, this one wouldn't have been as bad, but occasionally the exponents are just not friendly. Square roots come up a lot, we're going to see in applications. So just to recap on what we did on this entire problem so far was we had to do exponent surgery, essentially. So the square root x here turned into x power a half. We expanded all these things, but now their exponents here have to also have a denominator of 2. So power 2 turned into 4 halves. Power 1 from the two middle terms turns into power 2 over 2. And finally, this is what it looked like when we FOILed. We're just multiplying here to here and so on to get these terms. But after doing all of that, we can now say that f of x equals, coming down here, we did all the hard work on the prior steps, and we're just going to say for x to the power of a half plus 4 halves gives us 5 halves. That's where we're using this rule here by the red dot. We're finally adding up the exponents. The exponents were just nasty to deal with in the first place. Over here, we'll do it again. It's going to be minus 15, x to the power of 3 halves. Now I'm just copying 9x power 1 half. So after all that work done, looks like I still need a little bit of space on this. But after all that work being done, we're about ready to, oh, hang on, I have a problem with my thing moving down. Let's see if we can take this strategy. Okay, sorry, lost my train of thought trying to fix the formatting. But here we are finally at this last stage. All we have to now do is differentiate to that whole function. So in black is the function. Finally in blue, here's the derivative, f prime of x. Now, it's not too different from what we've seen before. For example, this is a more typical problem. Our first example of the day was an implied problem where the constants got a little bit nastier, the coefficients this time. And now in our current problem, same kind of deal that we're dealing with, except this time the exponents are a little bit nastier to deal with. So let's work this out really carefully. When we differentiate the first term, 4 gets multiplied by the old exponent, 5 halves. The new exponent is always 1 less. But if you're looking at a 5 halves, 1 less means subtract 2 over 2. So the new exponent here will be 3 halves. So that's what happens to this full first term right here. It just turns into all of that. We should pause right here since the pattern is just going to continue on the next terms. But did that make sense on the very first one? Yeah, exactly, Doug. On the
So we
5
just take,
halves,
so we just take the denominator minus the numerator.
exactly what we're doing. Yeah, I think that's a great way to visualize it. So for example, on this one, we're going to have to subtract 1, but we're just taking 2 minus the 3. That one would turn into a 1 half, exactly. Other questions or comments? Okay, let's try it out all over again. Oh, I thought I hit the eraser. There we go. So now on this term we're working on, first we're using the constant multiple rule. Negative 15 is multiplying, so that means it just gets copied down, unaffected by differentiation. Gets multiplied by the old exponent, which was 3/2. And on the new exponent, we're subtracting 2 over 2. It'll still have a denominator of 2, but like Doug mentioned, the pattern here is you're just sort of taking 2 away from the numerator and maintaining the old denominator. So new power 1/2. So if you look at that really closely, not too different from what we did in the first term, just slightly different numbers. Looking all right so far? Okay, one last one to go. When we differentiate this one, the pattern, same as always, becomes copy down the 9. I should go back to blue. Here we go. Copy down the 9. It gets multiplied by the old exponent, 1/2. New exponent is 1 less. And this one looks really weird because we're subtracting 2 over 2 from 1/2. So subtract 2 from the 1. We now have a -1 divided by 2. So the new exponent is negative, but you know what? That's completely fine. I'm not worried about changing that to a positive exponent or anything like that. You're perfectly welcome to use answers just like that. One thing we would have to do, though, is simplify it. So I still need to multiply my constants together here, here, and here. But we now have the derivative. So working through the multiplications, 2 divides into the 4, so it's just 2 times 5. So 10 x power 3/2. Nothing fancy on this one. 3 by 15 is -45. Still divide by 2. New power of x is 1/2. And nothing too fancy on this one as well. This is just a 9/2. X to the power of -1/2.
So
That's
we're
a
doing all,
nasty one.
so we're doing all these over 1, right? So 4 over 1, -15 over 1, 9 over 1.
Exactly. Yeah, that's a great way to visualize these. So your fractions are really being multiplied in that kind of way. Yes. Other questions at the moment? Okay, well, we did it, folks. This one is really, really nasty. I like these kinds of problems, but occasionally we have to see how these ones go as well. So there's a couple of these in the notes. Good news is part C looks like it's kind of a break from that. So really fast derivative as well. And I think that's how the actual problem set goes. Our author is a little bit weird when he writes out our problems. From problem 1 to problem 2 to problem 3, sometimes problem 1 is easy, but problem 2 is really hard, and then problem 3 is really easy. That's kind of strange. So it's not a bad idea when you look at your problem set to kind of cherry pick, starting off with which ones look more approachable and working your way up in difficulty. But let's give this a try next. This function is y equals t to the power of -2/5. Kind of an oddball function, but we can still differentiate that one. Here, you could just call this y prime if you prefer, or if we were using Leibniz notation, we would say dy. We're expressing the derivative of the y function. Then we would put down dt. This is to say we're differentiating the function with respect to t, because the variable indicated is t. All this is y prime, so if you prefer to call it that, I'm totally okay with it. So dy dt in this problem, you know what? This one's kind of all set and ready to go. We would take our old coefficient, it's -2/5, write it down. It multiplies t, and anyone spot the new coefficient of t? That would go right here. Close, but it turns out it's not going to be -3/5. You're on the right track, though. It will involve a fraction with denominator 5. Good call. This one turns into a -7/5 for the exponent. Absolutely. So that's the name of the game. no matter how weird these exponents look, sometimes they can be pretty weird, it always goes exactly this way. Take the exponent, it's now a coefficient. If there was a number in front of t, that coefficient would have multiplied it. Then we're always subtracting 1, but 1 looks different depending on the context. On this one, we're really subtracting 5 over 5. So the old denominator is still 5. And visualize taking -2 minus 5, essentially, to get that -7. So that's how part C goes. And then suddenly, things go wrong in part D. We can't just differentiate that function in that format. Most people wouldn't without taking extra care. That's way too much mental mathematics for me. Yet part C, we could. Here's the reason behind all of this. Let's recap on the power rule. So it's up there in the notes, but let's just restate it so we're not scrolling up and down. The power rule says, if you take the derivative with respect to the variable x of a power function just means it's a variable x to a power, let's call the power n, then you get n, that's our new coefficient. So that's what happened, that's our old coefficient coming down. So much like the -2/5, it came down here. If it's an n just comes down. We go x to the power of 1 less, so n minus 1. Again, that's what we did on this one. It was -2/5 minus 1 gets us to -7/5, But there's a defect, well, not so much a defect, but there's a restriction on this power rule. Let's state it right here. X, let's say it more clearly, the base x must be in the numerator. The top of the fraction. Numerator is a long word. If it's not in the numerator, the base x, then this power rule doesn't actually go this way. And so that's why we have some troubles with that function down below. It's a little bit of an oddball one. A might have been area, S could have been a side length of something, but it's a totally made up function. Think of S as being the x in this problem. So our variable is now in the denominator everywhere along the way. We need to do some corrections on this one so we can actually use that power rule. So that's the trouble with this situation here. And that means, again, this is a lot of recap on essentially exponent laws. If you feel like you need just extra practice on that, on the Moodle webpage, you have exponent laws review material and a little worksheet as well to go along with it if you feel you may need extra practice. But we'll state what we're about to use right here. So we need to bring that base S, think of that as the x in the problem, up into the numerator. And the way it works is, if you have 1 over x to a power of n can be any power whatsoever, then this is equivalent to x to the power of -n. So that's going to be our first exponent law to use. Then we have some issues with that thing right there by the red dot. But we can state another formula that says this. The 5th root of x to the nth power goes like this. We take n to the nth power and just divide by 5. So the takeaway on this one is, anytime a root comes up, the root, whether it's a 5th root, cube root, or square root, always fills out the denominator. That's kind of what we were saying up here in the notes, if we scroll for just a moment, where we were saying the nth root is equal to x to the power 1 over n. The 5th root is x to the power of 1/5. But if there's a power here on the red dot, it fills out the numerator. So for example, if this one had a power 2, right there, then it would have turned into a 2/5 in that kind of way. So the index of the root always gives you the denominator with the exponent. So back down to this problem, that's got a lot of work we have to do on it, but this is the end of the day, what we're going to do. This is going to turn 5th root of s power 3 into s to the power of 3/5 in the end of the day. Well, we have a couple things to correct, and let's work out this in stages. I want to start with leaving the first two terms just the way they are. So A of S equals -3 over S power 4 plus 9 over S cubed plus 1 over, not sure why my screen went black. I'm not sure if you can see that in Zoom. My screen blacks out sometimes around this part of class. Probably the laptop getting too hot. But this part right here just turns into S to power 3 because it's a fifth root by the red dot. We divide by 5 there. So I used these rules right here as the first step. Any questions on the first step, folks, for A of S? Okay, then we have power rule drama where our variable S needs to be in the numerator, much like what we have here, x power n. So now we're using these ideas right here. We can take the whole function and now say A of S equals, if there's a coefficient in the numerator, we just write out the numerator, -3, S to the power of now -4. So if S goes from denominator to numerator, like this, all we do is we change the sign of the exponent. Going down the line, this one will be +9, S power -3, plus S power of -3/5, coming from that last term. So a term-by-term basis, we just move the base S up into the numerator. Also, for me, another thing that's tricky about this problem is I'm attempting to write S in a way that doesn't look like the number 5. These are not the best choices of variable. I hate S as a variable. Okay, so we've done all of our exponent law surgery. And then that just means we get to use the power rule as stated here by the red dot. So going left to right, we'll say A prime of S, because now we're talking about the derivative. I might as well switch to blue. I think we're using that for our color. A prime of S is going to be, first we take the -4, multiply by the -3. For double negation, we get +12. S to the power of 1 less. Any volunteers for the new power here on that variable S? Good call, Dana. This is going down, so -5. For me, this is actually kind of tricky because, well, it's a reminder that when exponents are, say, positive like this one, we expect them to be going down, so it's now power 3. But if you make that exponent negative, it does make it a little bit foggy. So if it's a -4, it still goes down like before, but now it's a -5. So in other words, this power rule that stayed here works no matter what. The only major thing that's required is base x had to be in the numerator. So S power -4 makes a power rule work. But over here with it in the denominator, it's not going to work in that exact format. But let's keep on going. On the next step, we take -3 multiplied by 9, so it's -27. The new power of S is 1 less, so this is power -4. And one last term to go. Same exact pattern. The exponent, -3/5, is turning into a coefficient. But now the new power is take 5, subtract by 1, which is subtracting 5 over 5, and we get -8/5 altogether. So for that function there, it's a challenging one to differentiate in that format. But once we put it down to this format by the red dot, it's just like all the others, like the first example we did, except the exponents are a little bit weird. That's part of what we're getting used to. Well, we did it, folks. I feel like this one is a pretty challenging one in this set as well. Any questions at all with working through that one? Okay, looks like we still have a little bit of time, but I'll make sure we cut this off on a point that makes sense. Let's see. Part E, I think we can do. Part F, maybe. We might end class today on the conclusion with part E, just see where we end up on, which means we'll finish off these notes when we come back on Wednesday's class. But here's our next one to try out. And part E has the same problem as some of the prior parts. If things are being divided in this way, I don't have any formulas for that that's going to work out. The warning on this one goes like this, or I think we're calling this a caution. Let's use caution again. Caution. So if you have a function in the numerator like what we have here, well, let me start with a sentence. The derivative of a function in the numerator, like what we have up by the red dot, divided by some other function in the denominator, is not f prime divided by g prime. That deserves another exclamation mark. There is a way to differentiate that, but it's through something called a quotient rule, the next section, 3.4. And this is a problem where we actually wouldn't even use the quotient rule on this one, even in section 3.4, because we can fix that function just by taking root x and dividing it into all terms in the numerator. So that's going to be our approach on this one. One thing I did notice is there's a typo on this. Sorry, I didn't catch this earlier. Let me see if I can fix that. My typo was right here. That should have read f of x, not v. Sorry for missing that one. I tried to proofread these notes, but that was my mistake. So I guess it was invisible to me this morning. It didn't catch that one. So with a quick correction, if this is our function f of x, we can now say f of x is also equal to, take that denominator of root x, it divides into all three terms above. So it's now x squared divided by root x plus 4x divided by root x minus 1 over root x. Now we have several things we have to correct here. For example, well, we now have three functions that are type f over g, but we can simplify these kinds of things. We'll use the idea that root x is just an exponent, x power 1/2. So we'll put power 1/2 down below there. That means we're going to write the power 2 as a power 4/2 as well. So everything has denominator 2. But another exponent law we need is if we take x to the power of m, divide by x to the power of n, that's essentially what we're doing here with interesting powers. In this configuration, the exponents would subtract. So we would take the numerator exponent m, subtract the denominator exponent n. So it always goes off in that kind of format. So let's start rewriting this again. So that we can divide, we'll write x power 1/2 for our root x's. This now needs to have a denominator of 2, so the power 2 becomes 4/2. And that makes it so once again, we're compatible right here. They both involve denominator of 2. So when we go to use this rule, that's just going to be an easier computation if we line up our fractions just right here and now. Any questions first with redoing the first term there for f of x? Okay, well, that was so fun. We'll just do it all over again. Over here, where the red dot is, visualize that as a power 1. If you do that, you can now think of this as x to the power of 2 over 2, which is still 1. The root x turns into power 1/2, minus, and last one to deal with. This is 1 over x power 1/2. For that last term right there, we'll be using this rule with the black brackets right here. Something in the denominator, we can promote up to the numerator. It's just that the new exponent here would be negative 1/2. So last couple steps, and we're about ready to finish this off. But one thing you might notice here is everything in black is the original function. I can't put a prime on any of these because we're not even differentiating yet. We're just simplifying the function so that it's in the right format for differentiation. So still at f of x, going down the line, we're subtracting our exponents. So 4/2 minus 1/2 gives us x to the power of 3/2 on that first one. This is plus 4. 2/2 minus 1/2 gives us x power 1/2. And on this one, we promote up to the numerator, so it's negative x to the power. That 1/2, which was positive, turns into now a negative 1/2. So that's the function we really want if we're going to calculate the derivative of f. That's what happens in a lot of these problems where algebraically, maybe something's been factored or something's been added together as a fraction. We have to undo all that because our differentiation formulas prefers functions in this format, just fully expanded out. But now after doing all that work, here's our punchline. We get to now finally say we're calculating the derivative. So this is f prime at x. Power 3/2 comes down. We subtract 2 from the numerator there, 3, to get 1/2. Visually, what we're doing is we're taking 3/2, subtracting 1, which becomes 3/2 minus 2 over 2, giving us the 1/2 here. Then it's rinse and repeat. It's 4 times 1/2. So when we do that, we'll get plus 2. But just for the sake of conveying this in the notes, I'll write in this extra step. So old coefficient of 4 gets multiplied by the old exponent, 1/2. Any volunteers for the new exponent? That would go right here.
Negative 1/2.
Yeah, absolutely. Thanks for catching that, Dana, or calling that out, I mean. So you're subtracting 2 over 2, and you'll get a negative 1/2. Good call. So that takes care of that first term. Observe there's still a little bit to simplify here. If you put plus 2 right in that spot, I'd say that's just fine. But we're learning this stuff for the first time, so I'm trying to add just the extra details of how this would go. So next, this is a negative 1. I'll just convey as a negative sign, which multiplies the old exponent, negative 1/2. So altogether, if you just put positive 1/2, I'd say that's great. I would take it to mean you're visualizing negative 1/2 times a negative 1, and that's double negation for a positive 1/2. But for the sake of the notes, we'll write down this as a paper trail. On x, we started with negative 1/2, subtract 2 over 2, and that turns into negative 3/2. So that's finally our derivative. We just need to do a couple simplifications. So this turns into the derivative of f at x is 3/2 x power 1/2 plus, first simplification is that turns into a 2, x power negative 1/2. Double negation here gives us plus 1/2, x to the power of negative 3/2. Once we get to this answer, you could convert that x power 1/2 to square root of x if you really wanted to. You can make that power positive by dropping x down to the denominator. There it would turn to a square root of x as well. And you could do a bunch of things to this thing, bringing it back to the denominator and so on. But I'm always okay with it at that step. There's no special algebraic formats that we need if all we're doing is differentiating. What we did, folks, this is a lot of practice on doing derivatives. We'll do a little more on these notes when we come back on Wednesday's class. And then the major thing we'll be doing Wednesday as well is we'll jump into these notes, section 3.4, understanding the product rule and the quotient rule. They're really not too bad, but everything just sort of builds in stages. So I'd say the best thing to prepare for section 3.4 on Wednesday is practice some of these in the web assign and the reading, and you'll be in really great shape. Well, any last questions at all, folks, before we call it a day? Okay, well, I'm going to take a quick break. And then again, if there's further questions at 3:30, that's when my office hours will start. Have a great afternoon, folks, and I'll talk to you all later.